Hello. In this video, students will learn to recognize resonance forms and to convert one resonance form to another. Resonance explains inadequacies in bond line structures. When one bond line or Lewis structure does not fully explain the bonding or distribution of electrons in a chemical structure. To illustrate this, let's start by drawing possible Lewis structures for the given molecular formula. CnH4 with a positive charge on the whole molecule. Go ahead, start working on some possible structures and come up with at least one structure. Keep in mind that the structure you come up with must have at least one atom which has a formal charge of +1. Also realize that this formal charge cannot be on the hydrogens. It must be either on the carbon atom or on the nitrogen atom. Okay, these are three possible Lewis structures that students enrolled in our first semester of the organic chemistry series came up with. Please go ahead and verify if one of these structures is what you got. Now that we have a few possible Lewis structures for the given molecular formula, let's try to establish how each one of these is related to the other structures. Comparing structures A and B, notice that there is a difference in connectivity between the two structures. In structure A, the carbon atom is bonded to 3 hydrogens and the nitrogen atom to 1 hydrogen, while in structure B, the carbon atom and nitrogen atom are both connected to 2 hydrogens each. Since there is a difference in connectivity between these two structures, these are related to each other as constitutional isomers. Now let's compare structure A to structure C. Let's take a few moments to analyze the two. Notice that there is a difference in connectivity between these two as well, implying that A and C are also related to each other as constitutional isomers. Finally, let's look at structures B and C. How are these related to each other? Comparing the Lewis structures for B and C, it may seem like they have different connectivity as well. This is due to the double bond between the carbon and nitrogen in structure C. However, notice how each element is connected to the same other elements between the two structures. That is, the sigma bonded connectivity is identical between these two structures. Hence, we can conclude that structures B and C are not constitutional isomers. The double bond between carbon and nitrogen in structure C is the result of an extra pair of shared electrons between these atoms. Is this extra electron pair present in structure B? If so, where? Yes, it is the lone pair on the nitrogen atom in structure B. If we move this lone pair to the bonding space between carbon and nitrogen to create a pi bond, in addition to the sigma bond which exists between carbon and nitrogen in structure B, the result is a double bond. The final structure would then be structure C. The formal charges are calculated based on the bonding pattern of carbon and nitrogen in these structures. Hence, we can say that what's different between structures B and C is the distribution of electrons. In fact, this is the only difference between these structures. Similarly, we can go from structure C to structure B by moving the pi bond between carbon and nitrogen to make it a lone pair on the nitrogen atom. Pay special attention to the arrows used to show these electron movements. The tail of the arrow starts from the source of the electron pair, as in a lone pair or a pi bond, while the head points to where the electron pair moves. For example, in structure B, the source is the lone pair on the nitrogen atom, and this electron pair is moving to the bonding space between carbon and nitrogen. Hence, the tail of the arrow is at the lone pair on the nitrogen, while the head points to the bonding space between these atoms. Structures like B and C, which have identical connectivity and only differ in the distribution of electrons, are called resonance forms. Resonance forms are drawn separated by a double-headed arrow and are enclosed in square brackets. Resonance structures are not real structures. An individual resonance structure does not accurately represent the structure of the molecule. Resonance structures are not in equilibrium with each other. There is no movement of electrons from one resonance form to another resonance form. Resonance forms are not isomers, as we saw in the case of structures A and B, as well as A and C earlier. Isomers differ in the arrangement of both electrons and atoms. There is a difference in connectivity within the molecule. Resonance forms, in a sense, are different ways to represent the same molecule. This raises an important question. Which of these structures is an accurate representation of this molecule then? The answer is neither. The true structure is a composite of both resonance forms and is called a resonance hybrid. The hybrid includes characteristics from all of its contributing resonance forms. To draw a resonance hybrid, start by first drawing a skeleton structure. This is the connectivity in the molecule that is preserved between all resonance forms. For this particular example, this includes all sigma bonds between all the atoms. Now identify the difference in bonding between the two structures. For this example, the carbon and nitrogen are connected by a single bond in structure B, while these atoms are connected by a double bond in structure C. The hybrid structure should capture an average of the two scenarios. The average of a single bond and a double bond is a 1.5 bond. We show this by including a dashed line to indicate a half bond. Charge comes next. Between the two structures, the positive charge is either on the carbon or on the nitrogen atom. To capture this scenario, we include partial charges on each of these atoms, as seen in structure 1. Alternatively, we can enclose the structure within square brackets and show a positive charge outside to indicate that the charge is spread over the delocalized area. Resonance allows certain electron pairs, and hence the resulting charge, to be delocalized over two or more atoms. This delocalization of electrons enhances the stability of the molecule. A molecule is thus said to be resonance stabilized.